Let's see this case. A smooth ring A of mass m can slide on a horizontal fixed rod. A string tied to the ring passes over a fixed pulley B and carries a mass 2m as shown in figure. So this rod has a mass of 2m and this ring over here has a mass m where this angle is given as theta. At the instant the ring and the pulley makes an angle of theta. Show that if the ring slides with a velocity v, then the block descends with v cos theta. In the first part, we need to show that if this slides forward with v, this goes down with v cos theta. Second part में we need to find the acceleration with which the ring starts moving when the system is released with theta is equal to 30 degrees. So in the second part, basically we need acceleration of both of them. Let's start with the first part. The first part of this concept is actually based on a concept of string constraint, where it's a very simple thing that in these cases length of the string is constant. If length of the string is constant, let's say the front part of the string moves with x1 forward and the back part moves with x2 forward. Another fact over here is that string in these cases remains tight. So point number 1, if length is constant, and point number 2, if string remains tight, then x1 must be equal to x2. Differentiated dx1 by dt should be equal to dx2 by dt, and rate of change of displacement gives you velocity, so v1 must be v2. So if this end moves forward with v2 and that end moves forward with v1, then v1 must be v2. Or you can actually say a statement that the component of velocity along the length of string always remains constant. Now let's see how do we use it. Let's say the block goes down with vc and this moves forward with v. See, this is the string over here, this is the string. So we need the component of velocity along the string. As you can see, vc is already along the string, but v is at an angle of theta. So we'll resolve v into two components. One is v cos theta, another is v sin theta, like this. Now as I stated above, the component of velocity along the length of string remains constant. So vc must be equal to v cos theta. This is my equation number 1, or this is the first part which we needed to prove. One more thing over here, if it moves forward with a and if this goes down with ac, then differentiate velocity, you will get acceleration dvc by dt would be equal to dv by dt times cos theta, or ac must be equal to a into cos theta. Now let's find out the accelerations. Let's say this is the setup where this block moves forward, this ring moves forward over here with an acceleration equal to a, and this block moves down with an acceleration equal to ac. The string is tied with a tension equal to t, such that in this case we have three variables t, ac and a. To solve three variables I need three equations. The first equation I have is, let's say this block has a mass 2m, so 2mg acts on it downward, tension T acts on it upward, so that for the first block net force can be written as mass into acceleration. Net force is 2mg minus T is mass 2m, acceleration AC. This becomes my equation number 1. If you see my second equation, see, this is the horizontal setup where this is the bead and it experiences a tension T over here at an angle equal to theta. So that this tension T can be resolved into two components, one T cos theta, another T sin theta, where this setup moves forward with an acceleration equal to A, such that I can say for the second block net force is equal to mass into acceleration. So T cos theta must be equal to mass into acceleration. T sin theta along with gravity acting in the downward direction gets balanced by normal reaction in the upward direction. So I have two equations. One is 2mg minus T is 2m into AC. Second is T cos theta equal to MA. I've already derived the third equation. Third equation is actually AC is equal to A times cos theta. You have to solve the complete problem at theta is equal to 30 degrees. Solve it, you'll get acceleration as 6.8 meter per second square. That's the answer.